Hello everyone, Jim Malis again. Let's get some work done. Essentially, let's proceed further. We had done chapters 1 and 2 from the Katz book. We had done chapters 1 and 2 from the Katz book the last time that we were together, done some problems. Let's take a look at let's try to take a look at chapters 3 and 4 as we proceed with this right now. Let's see what we can say here. Okay, let me look at some of what is being said here. For chapter 3, we're going to try to do the following, chapters 3 and 4. Let me kind of make that the emphasis here. Let's see how the time permits it. I'm likely going to break this thing up a little bit, at the least. So let's see how it proceeds at different times here as we do this. So we're looking at trying to do some problems from chapter 3, problems 62 and 70 is where I'm going there, at least initially. And then from chapter 4, we're going to try to do these, 16, 19, 20, 30, 16, 19, 20, 30, 38, 39, 40, 49, 60, 68, 70. See how that proceeds. Let's see what we can do about it. So I'll leave this up here for a bit, eventually erasing it, but that's kind of the game plan for those two chapters, how we want to go with that. It's essentially the game plan there for how we're going to go with that. So with that in mind, let's take a look. Let's take a read at some of this stuff. Now you already saw me talk about vectors a little bit, and chapter 3 gets into vectors a bit. Let's see what we can do here. We're talking about 62 and 70. Let's see what we can say. For problem number 62, they are saying, let's see here. Okay, there's different things I was told here. Okay, some of these aren't even, I don't think I may have, let me just see. Forgive me here. There it is. All right. For 62, it is saying a glider aircraft initially traveling due west at 85 kilometers per hour encounters a sudden gust of wind at 35 kilometers per hour, directed toward the northeast. What are the speed and direction of the glider relative to the ground during the wind gust? The velocity of the glider with respect to the ground is the velocity of the glider with respect to the wind plus the velocity of the wind with respect to the ground. So I guess we're going to take a bird's eye view of what's going on, and then from there kind of proceed to get this thing under control and see what we can do about it. So with that in mind, let's see what I have here. Number of ways this can be played. Let's see exactly how I want to do it. Let's draw like a kind of a rough drawing of it first. Let's kind of follow the book vis-a-vis that. And it's looking something like this is a bird's eye view of the airplane, I guess you could say. That's the back end of the airplane. That's the front, the whole thing here. It is going at 85 kilometers per hour. Now we're going to take what we've learned about vectors, or at least some of it, hopefully all of it, and make some sense out of this. They are telling us, now this is a bird's eye view. So you're on top. You're in a helicopter way on top or some other airplane or aircraft. And we're basically told that north is that way, south is this way, east is this way, and west is that way. Sounds good. Now, in addition to all that, while this is happening, you've got the wind hitting it, not as strongly as this is getting hit, obviously, as this is propelling itself, but you got it as 35 kilometers per hour. At a 45-degree angle here. So there's a tug of war going on in a sense. There's somebody, this thing's being tugged that way, but it's also being tugged that way by the engines. The engines are putting it that way. The wind is hitting it that way. There is a vector sum about to take place. Vector sums don't add up like money. We already said that. You're not going to add this thing up like it's money or something. So, or kilograms. You're not adding it up like money or mass. You're adding it up like it's forces. Forces, accelerations, velocities, those add up as vector sums. So, what's going on here? Well, I guess you can kind of abbreviate a lot of what's going on by saying, I tell you what, let me just draw this guy, the airplane, as a ball. You'll see me do that a lot, I guess. This right here is 85. And this right here is 35. Now do a vector sum there and you're done. It's that simple. It's a 45-degree angle here. 45-degree angle there, and there it is. I mean, I'm going to do a vector sum right there. So basically, you're going to break this up into a component down here. See, a lot of what happens with vectors, let's say you had a vector like this. Let me just make something up here. This is a vector like that. As one of my TAs kind of brought up to me very, very beautifully, you don't really need to draw the vector symbol if you've drawn the arrow. There's the arrow. It's already implied as a vector. Just put a magnitude. It makes a lot of sense. So there it is. There's a vector. Whether you get to it or not, that's not the biggest deal in the world. But so if you've got something looking like that, here's a vector. There's a component a sub x, and there's a component a sub y. And this is a right triangle, 90-degree angle, and that's theta. Starting to look familiar? Yeah, we never really get away from the Pythagorean theorem, you guys, when we're doing this stuff. So let's see what we have here, guys. If it's looking like this, what's going on? Well, I know that the cosine of theta is adjacent over hypotenuse. I know that the sine of theta is opposite over hypotenuse. I know that the tangent of theta is opposite over adjacent, etc., etc. This is pretty useful because once I get these two ratios, I can do an inverse tangent and find out what the angle is. I can actually find an inverse sine and find the angle. Inverse sine of this, if I get the inverse sine of this, I will get the angle theta. Inverse cosine of that, I will get the angle theta. Well, let's talk. This right here, AX equals A cosine theta, and AY equals A sine theta. You can resolve vectors by taking the cosine, usually taking the cosine. It's not set in stone, you guys. I mean, when you got to look at the components. All kinds of trigonometric functions can get you the same answer depending on how you are relating to what's going on there. I'll make a long story short. It's not really set in stone, but usually the way they set it up is that if you deal with the cosine function, you can work with it and get the x projection. If you deal with the sine function, you can work with it and get the y projection. That's what I did right here. This is essentially how you're doing a lot of stuff to resolve what's going on with the vectors, you guys. There's a lot of what's happening. Well, okay, that's all well and good. What are we doing here? Why don't you find out what's going on east and west? Why don't you find out what's going on east and west, find out what's going on north and south, and build it like a triangle. Remember, vectors add like triangles. They don't add like money. It's a big thing. So let's see what we can do. We made the statements that we made right here. Let's proceed. Summation of the x. I'll tell you what, I'm going to say going that way is negative. Going to the left is negative. Going to the right is positive. Going up is positive. Going down is negative. Fair enough? All right. Tell you what I'm going to do. That's going that way, so it's negative 85. Going to the right, 35 times the cosine of 45 degrees will give you the projection. Will give you the projection this way. You know, I'm looking to find a projection going this way, and I'm looking to find a projection going up. So let's find this guy right here. This guy right here is going to be 35 cosine 45 degrees. That's going to be this guy. This guy right here is going to be 35 sine 45 degrees. So there you go. Two different situations here, guys. If you just take a snapshot of this guy, you got the 35 here. You got the 35 cosine theta. Theta happens to be 45 degrees. Here you got the 35 sine theta. Theta happens to be 45 degrees. And that's what you're looking at. And that's what I'm looking to try to resolve here. So as we do this, we got negative 85 plus a positive 35 cosine 45 degrees. Okay, guys, I just want to see how visible this is. It's not too bad. White chalk seems to be a little bit better. Maybe the other stuff's better for highlighting. But anyway, so you're right here. And you're right here. You know, at a bigger level, you're just basically saying, if that's 35, as we said, it's 35 cosine 45 degrees, 35 sine 45 degrees. This is the 45 degree angle. It was the 45 degree angle right there as well. So that's kind of how some of the game is getting played. Sine of x, the summation of x, Greek letter sigma, is telling us that. See what else we can say here, guys. Summation of the y's is just straight up, guys. That's the only thing going on here, this guy. There's your y. I got no other y component here. It's just going straight up. Got no other y component here. So that ends the matter, actually. I mean, you got, well, I'll make a long story short. That right there is the y component. That right there is the velocity, the Vx component. If we're going to do a V, you can do a V, A, B, whatever. You put anything you want for the vectors here. Let's just make a long story short. This is the y component. This is the x component. This is the x component. In totality, that's the x component. In totality, that's the y component. What does that mean? It means essentially this is v sub x. And it means that right there is essentially v sub y. And at that point, just put them together. I mean, do the mathematics here to get, forgive me, this is the v sub x, and this is the v sub y, rather. I'm sorry. This is the x component. That's the y component. And you proceed from there, basically. So when you do all the addition and everything else right here, you're going to get v sub x is negative 60.25 kilometers per hour. V sub y, grind this thing out. What do you got? You got this. There's a lot of ways you could play this at this point. You got these two right here. I mean, there's a whole lot you can say, actually. I mean, let's try to say a whole lot. How big is, what are we talking about here? How large is this vector when all is said and done when you do the vector sum? I'm not going to add negative 60.25 and positive 24.75 like I'm adding money. Doesn't work that way. I'm going to add them like vectors. What does that mean? Well, it means I got to put them into a triangle. Basically, this thing is going, here's your Vx going that way. Here's your Vy going up. Here's some angle theta. That's west, that's east, that's north, that's south. Remember, why did I put it that? Because this thing is negative, this is where the 60.25 is. Because this is positive, this is where the positive 24.75 is. So, I mean, there you go. You've got the Vy, you got the Vx, and this is going to be the V. How does that work? Same way it always works when you're adding, like you're adding triangles. You're adding things associated with triangles. It's the Pythagorean theorem. Take Vx and square it. Take Vy and square it. The sum of those two, square rooted, the sum of those two items, square rooted, will give you V. What are we talking about? Get an answer here, square it. Get an answer here, So get an answer for the V sub x, get an answer, all of this thing, whole thing, get an answer, square it. Get an answer here, square it. Add the two squares together and square root the sum. You're going to get V, you're going to get V right here. Take this guy, square it. Take this guy, square it. Add those two squares together and square root the sum. You'll get what V is. When you grind out those numbers, you end up getting, now let me kind of give us a little bit of room here. Okay, we saw what we just said here. We saw the initial look at it. We saw this too. So So let's just get rid of some stuff, guys. You've got the feature of being able to go back now. What's going on? Well, what's going on is when you do this, you do what we said, and we'll find out what the big V is. After you square all that, square one, square the other, add the squares together, and get the square root of that sum, you're going to get 65.14. You're going to get V is 65. You're going to get V is 65.14 kilometers per hour. Theta is going to be, let me give you the answer first, and we'll see why it's the answer. Theta is going to be this, north of west. What does all that mean? Well, V should be pretty straightforward. V is arrived at through the Pythagorean theorem. V is arrived at through the Pythagorean theorem. So you arrived at V through the Pythagorean theorem. How did you arrive at theta? Got a question for you. This is theta. That's west, that's east, that's north, that's south. It is going west, it is westbound, sort of, and northbound, sort of. Here's west, here's north. It is 22.33 degrees north of west. That's theta. How'd you get it? That's Vy, that's Vx. 24.75 divided by 60.25. Didn't we say that the tangent of theta was going to be Vy over Vx? Theta is going to be the inverse tangent of Vy over Vx. Watch what your calculator settings are. Vy is 24.75. The units cancel because they're top and bottom. They're going to be present. 24.75. The other one's 60.25. Find this ratio, then get the inverse tangent. It'll give you the angle that is associated with that ratio. Associated with the ratio of 24.75 divided by 60.25. At the end of the day, it should come out to the ballpark of 22.33 degrees. So that's this. That's this. Yeah, that's where it's coming from. That's how it works. Is there another way you could have done it? Is there another way you can report the answer? This is a good way to report an answer. As far as I'm concerned, it's a very good way to report an answer. Is there another way to report an answer? Yeah, I think so. I mean, the way you can do it is in component form, the way they like to. I mean, I've seen different ways. Just make sure you're answering the way they want you to answer it is, I guess, kind of the moral to the story here, guys. Is there another way to write it? Yeah. V vector. V vector equals negative 60. What does that mean? That means go to the left, not the right. Negative 60 I hat plus positive 24.75 positive 24.75 j hat. That means go up. That works too. You put kilometers per hour, kilometers per hour. Make sure that's there, okay, when you do that. And that's some of the discussion pertaining to that. It's a neat problem. Kind of a microcosm of a lot of things that you could see. Forgive me, guys, where the camera setup is. I'm always looking at the screen to look at myself, but I should look maybe into the camera a little bit more. But anyway, so forgive that a little bit. But we're fortunate to have the setup that we have. It's not ideal. I mean, the ideal is to have somebody in here live following me around as I'm going and zooming in on certain things. The resources, understandably, are not there to be able to do something like that. So we're fine. This is very good and tremendous amount of help for us that we're even allowed to do this during this crisis, to be able to get something like this under control, to try to help out everybody, try to help out the teachers and the students. So not ideal, but few things are ideal, but it should be good enough for you. You should be able to see what's going on. You should be able to hear me pretty well. They got a real good acoustic setup for us. And you can see this okay. On a bigger screen, this should be even more legible than there. I'm going to try to write as big as I can for you guys. Okay, so that is where we are. That is 62 from chapter 3. Let's go to problem 70 from chapter 30. I'm sorry, let's go to from chapter 3 rather. Chapter 30, would you love to have 30 chapters, you guys, in one semester? That'd be something else. Anyway, let's go to stay on chapter 3. Let's go to problem number 70. So with that in mind, 70 is kind of a similar, I don't know, it's all about vectors and stuff like that and what direction things go. Vectors add up a lot easier than you think they do. Let's see what we can say here, guys. Basically, I could tell you this, Mike. I can tell you a few things about vectors, and we'll see what we can say here. And they're playing a little bit of the same game I just had to play right now. Let me erase this stuff and let me talk to you a little bit about the information needed for something like problem 70 before we go there. All right, guys. I mean, some of the stuff we had said yesterday when we had spoken together and how that stuff all proceeds. Let's stay with it. I don't know how much more I should do pertaining to it, but you remember the stuff we had said, right? We had said that if you were going to do a thing called the dot product, you got a vector here, A, which is AX I hat. A sub x is a scalar quantity times a vector is a vector. Any scalar quantity times a vector remains a vector. Any scalar quantity times a vector leaves you with a vector. What it does to the original vector is it makes it bigger or smaller and or changes its direction in either make it bigger or smaller in the same direction, or it moves it in the exact opposite direction, collinear to it, but diametrically opposed to it, going in the other direction. Doesn't change the line on which the vector is. It'll put it one way or another on the line. If you multiply by a negative number, the vector will go in the exact opposite direction, diametrically opposite direction that it was going in originally. Collinear to the original vector, but in the exact opposite direction it's moving if you multiply by a negative number. If you multiply by a positive number, it stays, once again, collinear, but it stays on the exact same line, as we said, and exact same direction. Multiply by a negative, it goes in exactly the opposite direction. Simple as that. Gets bigger or smaller, and the negative or positive that you multiply it by will tell you it'll tell you if it orients in the same direction as it originally had, or if it goes in an opposite direction. Opposite direction of original motion, of original orientation. Opposite direction will occur when you multiply by a negative number. It's as simple as that. This is a scalar, that's a vector. Scalar, vector. Now, they usually don't go into the three-dimensional realm in this book. They do and they don't, I guess. Realistically, the three-dimensional realm is really the way you want to go because that's where everything is kind of working, or a huge part of what we're doing in physics, in engineering, and things like that are going to be in the three-dimensional realm. So you got something like this. And we talked about this a bit the last time we were together. We said A vector dot B vector means magnitude of A times magnitude of B times the cosine of theta, theta being the angle between the two angles, the angle between the two vectors. That right there was equal to AX BX plus AY BY plus AZ BZ, and that's a scalar quantity. Surprising, some beautiful mathematics to prove what it is. That's not our business right now, but it's there. We got it. And as we said, how this all adds up. So that's how vector, what is this vector really composed of? It's the sum, it is the vector sum. What is this vector composed of? It is the vector sum of these individual vectors. That vector plus that vector plus that vector. Fully resolved. Fully resolved. A vector cross B vector. I hat, J hat, K hat. We have this. We said that was kind of the pneumatic device, the memory device, pneumatic device. Mnemi in Greek means memory device. In other languages, even the M and N has something to do with cognitive function. Vaspomnit in Russian. Pomnit. Pomnit means to understand or something like that, or grasp. It's been a while since I tried to study another language. But, that whole idea, it's something cognitive. So it's a pneumatic device. It's a little memory trick you can play right here to get this right. Well, what we did last time was we actually just evaluated this. We said row 1, column 1, row 1, column 1, 1 and 1 is 2. It's going to be an even answer when you add them. That means AYBZ minus AZBY plus a negative J hat. Why is it a negative J hat? Well, row 1, column 2, row 1, column 2, 1 and 2 is 3, odd, so it's going to be AXBZ minus AZBX. Then the K vector associated with K vector, row 1, column 3, 1 and 3 is 4. It's going to be even. AXBY let's see here. Yeah, right. AXBY, BXAY. It's a mess, but this is pretty fascinating stuff. Bit of a mess that it may be, this thing right here being equal to this, this is equal to that. Let me just see how good the resolution is, guys, real quick here. Looks okay. Looks pretty decent. It's giving you this. Yeah, that thing right there is perpendicular to both vectors, A vector and B vector. This thing right here is perpendicular to both of the original vectors, A vector and B vector. It is perpendicular to both of those, and in a right-handed manner, it projects outward in a right-handed manner, perpendicular to both A vector and B vector, and it is as big as it is as big as the product of the magnitudes A and B times the sine of theta between the two vectors A and B. AB sine theta is the size of this thing, and this is how it's oriented. So if A vector was this way, and B vector was that way, and this is theta, the size of this times the size of that times the size of theta will give you the magnitude of A vector cross B vector. So it's just AB sine theta, like I just said. And the result, A vector cross B vector, let's call it C vector, is if you go A vector cross B vector, right hand, roll the fingers of the right hand toward B vector, start at A vector, go to B vector, roll the fingers of the right hand to B vector, A vector cross B vector, bam. As your thumb comes out, that is the result. I mean, this is a lot bigger. A vector cross B vector, bam. A vector cross B vector, bam, right out. Comes out like that. If they're right here, and the two are on this plane, and you had them, you had them doing something like that, you had the A vector and the B vector this way, A vector, B vector, cross them, bam, it comes out like this. Where's it located? That's pretty complicated. It's not, or here, or here, or here, or there. Really, what is, or there, or there. It doesn't have to be perfect looking. It does have coordinates. What are the coordinates of this thing? Coordinates of this thing are right here. It's crazy. Some beautiful mathematics proves it in a right-handed orientation. Why is this such a big deal? Because it occurs in nature. The mathematicians encountered things, the physicists and mathematicians encountered things in nature, and they tried to figure out the mathematics that would describe what they were encountering. This cross product is beautiful, and it's not made to irritate you, it's made to explain physical phenomena. You're talking about what kind of force a particle experiences, a charged particle would experience in a magnetic field. You're going to use the cross product. There's a lot of stuff that comes into play here. It's the way nature's set up. So that's kind of what you're talking about here. In addition to that, now if you did the other way, B vector cross A vector, put your right hand here, roll your fingers that way, it goes in. It goes in. They're the same exact magnitude. They're the same exact magnitude, but this guy right here is the negative of this guy right here. The same exact magnitude. What does that mean, the negative? Well, in a vector sense, the negative just means if the vector goes this way, its negative is the exact same, just the negative. The negative is the exact same size, only going in the exact opposite direction on the same line. That's all that it is. In general, if you go, negative, if there's a lot of stuff you could say, I guess. I mean, negative A vector is negative 1 times A vector. It's like this, is negative 1 times B vector cross A vector. I hope with the screen allows us to have this. Et cetera, you guys. Well, we've already been down this path in the other video, but I think when I did study a little bit of Russian, it said "Повторение мать учения." Repetition is the mother of learning. It's good to repeat this stuff sometimes too. Okay, so look at it. You know what's going on, you guys. We know how to do this. So with this in mind, let's take a look at this thing and see what we can say about it, and we'll kind of take it from there. Let's take a look at that problem, problem number 70. And with what we have read by now, by what we have read, and by what we know, by what we've discussed, we're going to be able to do it. You're always reading the book, guys, given the circumstances that we're sometimes in. If we read the book, look at the notes, I think we're okay. Still a lot of hard work needs to be done on it, obviously, but that's good for you as well. It's more rewarding when it's done that way. Okay. Number 70. Number 70, a vector, f vector equals 3 point, just do the setup while we're doing it, I guess. All right, let's see if we can. Okay, I'm trying to just see where I'm at in relation to what can get filmed here, guys. Let me just play it safe. 70 is right here. They are saying, for problem number 70, problem number 70, chapter 3, a vector, f vector equals 3.3 I hat plus 6.3 j hat is proportional to vector A such that f vector equals m a vector and m is a scalar. So for A, B, C, it goes like this. If A vector is this, what is m? Okay, so they're telling us, they're giving us this, guys. They're saying f vector, for it to be proportional, it's got to be a scalar multiple. Be really careful on this. It's got to work. If it doesn't work, it doesn't work, but then it's not, they're saying it is. So let's see if that's true. They are telling us that this f vector, by the way, is equal to a scalar, m, times the vector A. And m is a scalar. If A vector is 1.1 I hat plus 2.1 j hat, what is m? What's going on? Basically, they want you to take this, hopefully multiply this vector by something to get this vector. I don't know, it kind of stands out at us pretty good, you guys. Does 1.1 go into 3.3? Yeah, 3 times. Yeah, now I'm stuck. 3's got to be the magic number all the way across. 3's got to be the magic number all the way across. If it's not, we're in trouble. If you multiply 1.1 by 3, you get 3.3. If you multiply 2.1 by 3, you get 6.3. Oh, that one right there. We're good. That's it. Period. F vector equals 3 times A vector. 3 is that scalar. What is M? Draw A vector and F vector on the same coordinate system. See what we can do. Let's draw A vector. 1.1, 2.1. 1.1, 2.1 right here. Okay, that's A. The other one is 1.1 plus 1.1 plus 1.1. 3 times 1.1 is right here. That's 3.3. And 2.2 plus 2.2 plus 2.2, that's 3 times 2.2. That's up here. So we got this somewhere there. So we got that, and we got the other guy doing that. And there's That's A vector. That's F vector. One, two, three. I maybe made this a little too big. Who knows, maybe. We're not going to split hairs on that, guys. The big thing right here is they are absolutely collinear. They are absolutely collinear, and F vector is 3 times the size of A vector. And they're on the exact same line, and they are in the exact same direction because nobody got multiplied by a negative number. If you multiply by -3, it would be 3 times bigger, just like this one is, but it would be diametrically opposite to it. Collinear, but diametrically opposite to it. Okay? That is that. C, find the magnitude and direction of A vector and F vector. Are your answers consistent? Explain how you checked your consistency. This is fascinating. The component here is 3 times smaller than the component here. That component is 1/3 the size of that component. This component is 1/3 the size of that component. This guy's component in the x direction is 3 times bigger than this guy's component in the x direction. And this guy's component in the y direction is 3 times bigger than that guy's component in the y direction. Okay. 3 times bigger, huh? Yeah, we said this vector's 3 times bigger as well. So related to this, and again, all this is in the notes as well, guys, that I'm posting for you. Let's see what we can say here. I guess there's maybe an easy way to do it. Probably, there's the same angle. They're collinear. Doesn't matter which one you use. Theta equals the inverse tangent of the rise over the run. Rise over the run. .3 divided by 3.3. I don't know. Multiply this top one by 10, multiply the bottom one by 10, you got 63 over 33. Put 3 into 63, you got 21. Put 3 into here, you got 11. You got 21 over 11. That's exactly the same as the inverse tangent of 2.1 over 1.1. Multiply by a special one, 10 over 10, like 10 over 10 here, 63 over 33. Multiply top and bottom by 10. 10 over 10, multiply by 1, you got 63 over 33. You've got 21 over 11. Multiply top and bottom by 10 over 10. You get 21 over 11. 21 over 11, 21 over 11. They're all the same. Doesn't matter. Yeah, they better be the same. They're part of similar triangles. Look at the direction of it. Look at the direction of it. So what is it? Well, at the end of the day, it's 62.35 degrees . 62.35 degrees north of east. Yeah, remember now this is east. And that's north. That's south, that's west, this is east, that's north. Okay, north of east. Sounds good to me. What about the sizes? Guess the way I would do it is, compare, if you want the size of F, use the Pythagorean theorem. If you want the size of A, please use the Pythagorean theorem. Pretty fascinating stuff. If you actually do it, I mean, I think I did this a number of ways here. I mean, there's some of this stuff here. Let's have a look. Let's make sure I got it I'm on the right mark here. Yeah, should be fine. Should be fine, guys. The way it's going to work now, you can play this a whole bunch of ways. You could put the 3.3 is the size of F in the X direction, and 6.3 is the size of F in the Y direction. At the end of the day, that comes out 7.11, with the same directions, guys, with the same theta. Theta being this, 7.11 for this guy. And this, of course, is the direction that you'd put up here. Let me not write it again. You can see that's the answer. So there's the size, there's the direction. Okay. If they ask you for both, you got to give both. So I simply didn't write it down there formally, but right here, put it right there. Take all this, put it right here. This right here, you're going to do the same thing. You're going to go 1.1, 2.1, and that comes out to 2.37. And then put this right next to it. It's the same angle, same direction. This is 3 times bigger than that. Multiply this thing by 3, and you get, multiply 2.37. Multiply 2.37 by 3, you get 7.11. Yeah, makes sense. The corresponding components were at a ratio of 3 to 1. The big divided by the small. The corresponding components, comparing the big to the small, ratio of big to small, is 3 to 1. Every single component. Fx divided by Ax is a ratio of 3 to 1. Fy divided by Ay is a ratio of 3 to 1. Not surprisingly, the magnitude of F compared to the magnitude of A is a ratio of 3 to 1. And it works out perfectly. You can kind of do it a little more rigorously. I mean, you can also visualize that a little more, a little more rigorously if you want, in the sense that you could kind of say something like this in terms of the size. Is it true that we already just said, you're going to know the Pythagorean theorem like you know your name by the time you're done with this class? Didn't we say every component, is 3 times, this stuff's easier said than done, I guess. Or it is 9, but let me not call it 9. Let me call it 3 squared. Call that 3 squared. What's going on? What is this? If you look at it carefully, I'll tell you what it is. Interesting. That's a product. That's a whole piece of a number. You've got to be able to do this to be able to do what I'm about to do. Otherwise, you cannot do it. You can't do it with straight out addition. You've got to put the sum inside of a quantity. Once you've done that, you can manipulate as though the sum's not even present, as though it's just one piece of a number. Once again, this is much easier done than said. Pretty neat. M squared, I could have just put rather than a 3, I could have put an M, but I put a 3. But I could have put an m there. M squared, square rooted, is just m. M squared, all of that square rooted, is right back here. The heck is that? Equals m times a. 3 times a. Well, I guess the magic number here for m was 3. And 3 runs the show. F sub x is 3 times bigger than a sub x. F sub y is 3 times bigger than a sub y. F is 3 times bigger than a in the big picture. It's one big triangle. Here's the F triangle. Here's the F triangle. Here's the A triangle. This is M times AY. This is M times AX. This is AX. This is AY. This is A. This whole thing is M times A. You know, Fy so on and so forth. F is 3 times bigger than A. Fx is 3 times bigger than AX. Fy is 3 times bigger than AY. And that's where it's coming from. That's where it's coming from. For the problems, I want to kind of just show you on chapter 3 to kind of help you get acclimated to some of this stuff, you guys. Let's go to chapter 4. I'm probably going to break these things up into little pieces because I've made some long videos in other places as well, guys, and sometimes that almost has to be done. Other times, maybe it's a good idea not to do it. But here it is. You got all the stuff up here. Let me just check something very quickly. Okay, looks pretty good. Looks pretty good. Most of that is okay. Looks okay. All right. That will be it right now. And then I'm going to start with chapter 4 in the next video.